go to the regime where we have tightly bound fermion pairs, molecules. That's the Bose-Einstein-condensate limit. Or we can go further to the side where pairing is just a many-body affair. Pairing is just due to the presence of all the others that help you form the pairs.
How, in the BCS side, how do you see the vortices?
So the imaging works like the vortices on the BCS side have an extremely small contrast. Goes down with the gap exponentially. So what you can do is you can open up the trap and then move over to the BEC side to convert these fluffy pairs into tightly bound pairs.
After they expand?
Yeah, well, during the expansion, it's you know, you shouldn't do it too late because then everything is completely ballistic and you're just seeing the density profile of a single Fermi gas, which looks very boring. So you want to look at the pair wave function, not at the density distribution of single Fermi. So you have to move them over to the molecular side. As long as they are still connected as pairs, then they are very happily bound, and you see a Bose-Einstein condensate.
If you were doing this sweep quite adiabatically, then maybe you're seeing, is it clear that you're seeing the vortex lattice of...
Yeah, thank you. You have to read our papers. So, this is like such an old story that I'm almost getting mad at you not. So, here's the story. We do this sweep like in a millisecond. It takes 1 second for the vortices to form. Vortices are three-dimensional objects that stretch out through the entire cloud. And if you were just suddenly projecting this BCS kind of gas onto the BEC side, you would have some weird phase fluctuating beast, but not beautifully aligned vortices that stretch out along the whole entire axial trap. Where you have a long trapping period of 100 milliseconds, you have to wait forever for these vortices to actually stretch out in the line. So I'm not really mad. I'm just joking here. But this says.
No, now I remember. But
okay. So here's the story. It is not formed during the ramp. Okay. Yeah. Imprinted in your brain. Good. So here we have the equation of state that we want to have an access to. At high temperatures, we have a classical gas, where of course we know what it should look like. The equation of state should just look like a Boltzmann gas. And then as we cool down, we should at some point see the superfluid. Before that, there is an interesting question. Is it all the way a normal Fermi liquid before you reach the superfluid transition? Or is there something like preformed pairs that already form above the critical temperature for superfluidity, this kind of pseudo-gap regime? Well, that's under debate at the moment. And then at some point you reach TC, and in the superfluid state, of course, the question is what is the critical temperature, what's the superfluid energy, what's the critical entropy for forming the superfluid state? So all these questions would be nice to address by measuring the equation of state. Now, there have been 2 recent experiments that claim to have reached high precision in extracting the local equation of state for these gases. But there are several issues. For example, the Tokyo group, they assumed that they had a harmonic trap. Then they had to expand the cloud in order to not to saturate their camera. So they had to expand the cloud, assume that the expansion is hydrodynamic, and rescale back how the profiles should have looked like in the trap. Well, so that's actually a bit tricky and has difficulties. They do not disagree with the high temperature expansion for the equation of state that we know from theory, and they required a thermometer that came from another group in Duke, which I'm sorry to say is not correct. Yeah, so that is an issue here. Then in Paris, they had to assume harmonic trapping as well. They used an independent thermometer, lithium-7, which was swimming together with the fermions. It's a boson. It was happily in thermal contact. That's very good. However, unfortunately, this guy condenses at very low temperatures, and then it stops being a very good thermometer. They acquired the pressure and not the density equation of state. Essentially, the pressure is the integral over the density over the chemical potential. And it is just simply less sensitive to the equation of state than the density before you integrate. So that might be an issue. And then there are some technical issues with that method as well. So what we want to do is to just get at the density of the gas. As I said, okay, for a balanced Fermi gas at unitarity, the only energy scales are the Fermi energy and the temperature. So for example, the chemical potential has to read like an energy scale, E Fermi, times some universal function of T over T Fermi. That's how it has to be. Equivalent, you can write it as an equation for the density, which is contained in T Fermi here. N lambda cubed, you can call the phase space density at high temperatures, is some universal function of beta mu, chemical potential divided by the temperature. So we want to try to get this. Now, one thing that is really nice in these cold atom experiments, sometimes a nuisance, but here it's actually very nice, is that we have a trap. In a trap, provided that local density approximation holds, we can say, well, at each point we have a certain density, and that should correspond to the chemical potential at that point. And the chemical potential at that point simply tunes with the trapping potential, like the global chemical potential minus the local potential. That's very nice. In principle then, in one single shot of the experiment, you get the entire equation of state if you had infinite resolution. And if in the center you were at 0 temperature. Now, one issue with that method is, well, we can only measure column densities in these gases. So we take our imaging laser, shine it onto the atom cloud, and that laser, the atom cloud will cast a shadow onto our CCD camera. So it's the integrated density that we measure. The good news is that, well, we can go back from the 2D density to the equation of state using tomography via an inverse Abel transform. If you see this shadow, but you know that the cloud is cylindrically symmetric, you have actually an infinite information. It is as if you're looking at the cloud from all angles. So that's great. So you can actually reconstruct the 3D density. We know that the trap is cylindrically symmetric as well as we can make it because we have long-lived vortices in this trap. And so that's what we can do. We take our shadow images from the CCD, apply the inverse Abel transform, and reconstruct the three-dimensional density. So far, so good. Now, one more thing that we can do. If we know our potential now really well, we can sum over all equipotential lines. So we pick one potential that we're interested in and walk along equipotential lines, integrate that signal, and therefore get a very nice average signal for the equation of state. So that's the data then. We get the density as a function of potential after this equipotential averaging. So it's actually not very noisy. It's very nice. It works for any reasonable potential, this kind of method. It is not confined to harmonic trapping. Issue: how do we know our trapping potential? Many people just measure their power in their optical laser beam, the laser beam that actually confines the atoms and holds them in space. Measure how strongly it's focused and deduce the trapping parameters from there. Then also they take trapping frequency measurements in this trap and see that they roughly match. Now there are issues with all three things: power, waste, and frequency measurements. Especially if you start to shake your cloud to measure your trapping frequency, you bring it into new regions of the potential that you don't want to explore, and you might measure a wrong trapping frequency. So that's not so good. Instead, what you should do is use the atoms themselves as a probe for your trapping potential. In each experimental run, the atoms experience the same trapping potential. So that's nice. We can just sum up all kinds of density profiles from 10,000 shots if you want, with all kinds of different clouds. You might say, wait a second, now you're adding up data that has different temperatures, maybe different numbers of atoms. That's not a problem because they all see the same trapping potential. So you may just add them up. And then one thing is still true: at the locations where the density is the same, the potential have to be the same. So equidensity lines can be converted into equipotential lines.
Now, if you know, you see that in the first two lines, that it's parabolic along the axis and radial is Gaussian. And you should be able to know the shape of this equipotential to see if it's confined from the ellipsoid. So can you measure that and figure out?
Yeah, so exactly that. I mean, this is
to see how far you are from the harmonic.
Yes, absolutely. So we clearly see that we live in a Gaussian trap. We need at least the quartic correction to model our trap as perfect as we need it. But we are sensitive to that quarter correction.
So
if you just fit the bottom of our trap with a parabola, it's not right. It doesn't work out. And like it's maybe only a 10% effect, but you know.
No, 10% is quite a lot.
Yeah. So that is nice. We get the potential. We know the potential everywhere. Yeah. So I didn't tell you how we convert density to potential. Actually, we know exactly what the potential is. It's a harmonic trap. The atoms oscillate forever. We know exactly the trapping frequency. It's given by a magnetic curvature and not by a tiny optical beam. So we know along the axial direction exactly what potential we have. And that immediately labels all the equipotential lines for us. So that's how we get the potential. Good. Okay, so now we have to do thermometry. Good news are that we know the high temperature virial expansion for the strong interacting Fermi gas with two known virial coefficients. And so we can fit our density with this known virial expansion to get the temperature and the value of beta mu out of these profiles. And then we can just plot this profile. This is just a single shot. We of course average several times or to get a more accurate equation of that. We can just plot it onto our graph f of beta mu versus beta mu. And this is the virial expansion. So you see how the virial expansion is good at high temperatures, but at some point it breaks down. But here now we can use our own data to move further to lower temperatures. So we add lots and lots of data to generate the entire equation of state successively, approaching colder and colder data, using more and more of our data to fit even colder clouds. So here's now the virial expansion. I have zoomed out quite a bit now. This was the virial expansion, and now we can reach up to here. This is just f of beta mu from our data. Yeah, so 2 in fact. So the first one is 1. If you count that, then it's 3. But this, these two guys are real, so to speak, calculations. So we use those two. We can also not use the third one and then try to get an estimate for the third. But that was not our point to get that virial coefficient. Okay, yeah. So this is the equation of state. It looks very boring. We should compare it to the equation of state of a non-interacting Fermi gas by dividing by the known equation of state for non-interacting Fermi gas, just to bring out the differences. And well, that's what it is. If you squint your eyes, maybe you see something going on, but well, you have to squint your eyes. At least it is clear it is totally not a non-interacting Fermi gas. It deviates from the non-interacting Fermi gas right away, as given already by the virial expansion.
Orel Bulgak should see it because he's very good at it.
It's
Do you see the critical point?
I know where it is.
Do you see it?
It's good. So, how do we know that we are doing a good thing here? Well, we can also measure the equation of state for a non-interacting Fermi gas. And that was for me really the check that I wanted to see before believing any of these data points. Just trying the same method on the non-interacting Fermi gas. And I was totally amazed when we did this and really measured one, so to speak. We measured the equation of state of a non-interacting Fermi gas to the percent level. And I was like, okay, that's... Now I believe it. These data points have a controlled systematic error from the non-interacting Fermi gas. And only when I saw this, I was, okay, now let's play with this curve and see what it tells us. I should say, at very low temperatures, the equation of state has to reach a limiting value. The density divided by the density of a non-interacting Fermi gas has to go like 1 over some universal parameter psi to the 3/2. The simple reason is it's, at 0 temperature you have lost your temperature energy scale. The only energy scale is now the Fermi energy. So the density has to go like this Fermi energy to the 3/2, but well, maybe with some coefficient in front, and that's this guy. So it has to level off. And we start to see this saturation here, which is nice. I'll tell you in a second that this is not obvious for the pressure. I will also present slightly more convincing fit that gives us a new value for psi, which is actually very low compared to what has been around before, 0.36. And I admit I was a little scared about that. Then a couple of weeks ago, luckily, Michael Forbes calmed my soul and came out with a new upper bound for this value psi. It has to be smaller than 0.38. So that's good.
I don't understand the idea of this code. It constantly is dimensionless. So
Yeah.
what goal to introduce power law?
Sorry. This is pedagogically bad.
No constant.
This is pedagogically very bad. This psi appears in the question, what is the chemical potential of a Fermi gas? This is some universal number times E Fermi. That's how psi is defined from the energetics. And of course now if you look at the density, it comes in with the power law, 3/2. So don't worry, that is just because I didn't present it nicely. Yeah. So this psi has been around for a while. Okay, so now comes the crucial test. There is an independent, completely unbiased method around that Boris Fistonov and Nikolai Pugachev came up with, the diagrammatic Monte Carlo method, which essentially sums up, if you want, all Feynman diagrams, but not all, but they throw a dice to see which one to calculate next, in a clever way, of course, and they can go to high orders and find then a final answer for the equation of state in the high temperature limit already, and it is just very nice how well it agrees with our data in this high temperature region. They can now go even lower in temperature by essentially using dressed propagators instead of bare ones, and go beyond the high temperature regime and are still on our data extremely nicely. For finite numbers of atoms on a lattice, you get also an unbiased method that gives you data. It's of course not the thermodynamic limit, but it's interesting to see how this data behaves. Actually, already also shows a little bit of a kink.
I'm sorry.
See?
What did you say?
When?
You just said something and then you swallowed the word.
No, but it's interesting to compare unbiased methods with our equation of state. And I was just telling you that maybe you also see something happening here. Yeah, it's very nice. Then there are predictions for the critical point where the gas should become superfluid. We are not agreeing with this data point. We are in more agreement with another way to extract from the same theory to extract the bulk thermodynamic limit value. Still not quite on, but okay. It's at least now we can compare. We can integrate this equation of state to get the pressure. If you integrate the density over the chemical potential, you get the pressure. And of course, once you integrate data, your data looks beautiful and smooth. Yeah? So they're essentially, there's no point in showing an error bar here. But you also see it's featureless and really boring. Now, one thing that's obvious, well, maybe not obvious, but I will tell you, at zero temperature, the pressure should again be related to the non-reflecting pressure by this universal constant, 1 psi to the 3/2. But as you see, if you integrate something that is about to saturate, the integral will not saturate. It will take much longer until it actually saturates. So people who try to get this parameter from the pressure or from the energy will be in bad shape, because the pressure takes a long time to actually saturate to the zero temperature limit. Yeah, okay. So that is again the
Can I make a short comment?
Yeah, sure.
Because you were saying basically that the data are not in thermodynamic limit and stuff. Can you look at the previous plot? And we were comparing many theories which are supposed to... Yes, this one. Okay. The main problem with all the other theories is actually not the thermodynamic limit per se, but the fact that the interaction is not actually resonant. Because all those models were simulating something which is not quite resonant interaction. It was like something which produces resonant interaction in the limit of an extremely dilute system. And that was the main problem. So it was a kind of first principles unbiased simulation of something which is not quite resonant gas.
Oh, yeah.
And that's basically...
It was resonant, but it contained an effective range.
That's what I'm saying.
No, but it's still resonant because you can get infinite scattering length, but you get an effective range, and since you have finite chemical potential, you'll get effect from there.
Okay,
so resonant is the wrong word to say. You have an effective range.
Okay, let's put it this way. So because of the finite density, you
cannot
claim the unitarity. Let's put it this way.
They are about, could be as large as 10%.
So that's the origin, because otherwise it's kind of confusing why unbiased methods produce wrong result, because they simulate something not quite
yeah, okay.
in your system.
Thank you. Yeah. Okay. Mm-hmm. This is true also for these guys? For these?
Right.
Yeah.
Right. So it basically the problem with estimating the error bars.
Yeah.
The error bars which we were claiming with Ross, it turned out that our estimate of the error bar was wrong. We didn't have enough control to predict this systematics, because basically it's easy to control the noise, the statistical noise, but it's not that easy to control the systematics which comes from doing the limit.
Yeah.
Of course, it's our fault, but that's the explanation why we failed miserably.
Well, it's scientific progress, right? That's how it goes. There's also an experiment, by the École Normale in Paris, and it doesn't, lie on our data at low temperatures. High temperatures, we have nice agreement with them. This is essentially almost by construction, because both groups, use the Rayleigh expansion to clamp their profiles at high temperatures, but then we deviate at low temperatures. They appear to see here this kind of feature, but already the feature in the density that I haven't even told you how to squint your eyes to see it, if you integrate that, you get something smooth. So we don't see any kind of pinkiness in the pressure. So that's what it is. Okay, so now everyone knows for ideal Fermi gas, the chemical potential starts out at the Fermi energy at low temperatures and then just goes down quadratically with T over Tf. If you have a Fermi liquid, you should still expect that it looks the same way, but the energy gets renormalized maybe to some new value. Let's call it psi n times E Fermi, but then it also goes down quadratically, maybe with a slightly different opening curvature due to the effective mass. Now we get the chemical potential directly from our data. It's just a replotting of our equation of state. Because T over Tf we directly have, because it's just related to 1 over n lambda cubed to the 2/3. Density to the 2/3 is Fermi energy, and lambda cubed that has the temperature to the 3/2 unit. So that's very nice. We get a direct temperature scale. There is no kind of fitting or sweep from the BCS side to kind of match entropies or something. It's just a direct measurement of T over T Fermi. Mu over T Fermi, the chemical potential compared to the Fermi temperature, is just given by beta mu times T over T Fermi, so it's trivial, it's immediately there. So we can plot our equation of state and see what it does actually. It does not boringly go like a quadratic function. There is the downwards motion here in the chemical potential at very low temperatures, which we can put sense into it by saying, well, if we have a superfluid, of course the superfluid energy should be smaller than the energy that the gas would have in the normal state without any pairing. So we could say these energy scales, the limit of this quadratic kind of behavior and the limit that we actually have at low temperatures, that could be roughly the condensation energy, which would be given by the gap squared or so. Gives a quite reasonable value for the gap, which is 0.39 E Fermi. Very high, but as expected on resonance, to be very high. So that gives us also, if we try to fit our data with the expected kind of phonon T to the 4 behavior, then we can extrapolate to zero temperature and say, okay, so this looks like 0.36 or so might be the energy at zero temperature. All kinds of previous results placed psi s, this value here, up at 0.4, 0.42. So we are quite far away from that. One reason, again, is that usually people integrate over their cloud size, so that gives them the pressure or the energy, but all these quantities are average quantities, which wash out this behavior at the coldest points in the trap. And then they tend to get a higher value. There is a maximum, there is no direct thermodynamic meaning to that maximum, it's just a rough indication where I go from fermions to pairs, essentially, from single fermions to pairs, and well, that occurs at this point. Not saying that this is the critical temperature, but as a marker, the recent prediction by Gulko-Wingate is Tc over Tf is around there, 0.17. So I would claim this is the first observation of the energetics of the superfluid transition in thermodynamic data. Not needing any sweeps or vortices or anything, just probing the gas itself and seeing does it at some point look non-fermionic. That's what it is. As a guide to the eye, there is a theory by Zwerger and colleagues, which is essentially the first order Feynman diagram as far as I understand, which they sum up, and it has the same kind of shape. There's no reason that this theory should be then on our data, because it's just the first order Feynman diagram, but at least it gives the qualitative shape. They see this funny lip here, which comes from a systematic effect that they have in their theory.
It looks like distorted lambda transition.
It looks a little funny, it looks like a weak first order transition. It's
like falsifying.
Huh?
A picture falsifying the waves.
Something wants to get going there. So now we can also get the entropy, which is nice. The entropy, well, for this we would need the energy, the pressure, the chemical potential. Luckily, on resonance, the energy has to go like 3.5 times the pressure. That's simply because of universality. If you take the pressure is the derivative of the energy with respect to the volume for constant entropy. Constant entropy means constant C over Tf. So the only reason that the energy can change with volume at constant entropy is due to the density changing. And that gives you this 3.5 factor there. So we can directly plot the entropy per particle by plotting our pressure divided by density, temperature, minus mu beta, everything that we have, and this is the curve we get. In black, I've shown the entropy for non-rejecting Fermi gas, and it's kind of cute to see how close the data points of a strongly interacting Fermi gas lie on the non-reacting Fermi gas in this high temperature region. My hand-waving explanation for that is that, well, even if you have some renormalized Fermi liquid or something, you're not changing the way how entropy is stored in this gas. And so the entropy at a given T over Tf, if you have the same effective mass, should be roughly the same. Hand-waving explanation, but makes kind of sense. But down here, it actually deviates.
Simple-minded question. How in experiment you regulate pressure? You change pressure in the camera where is your cloud?
Essentially, it's the trapping potential, right? Yeah. So we have this nice trapping potential. Yeah. So locally we have.
This is governed by laser beams.
Yeah.
Potential.
Yeah.
What about pressure?
Well, the pressures, you just throw in lots of particles into your trapping potential. That gives you a certain chemical potential, a certain local energy, a certain local pressure.
So you regulate number of particles in the
yeah, so to speak, yeah.
Not the pressure in the camera or something.
No.
It's like atmospheric pressure.
Nice, yeah. It's like atmospheric pressure, yeah. Again, it's interesting to put here the first order Feynman diagrams on there just as qualitative guide to the eye. It also shows a dip down here at the lowest temperatures coming from the superfluid. We can look at the heat capacity. This is the heat capacity of a non-reacting Fermi gas. It's actually calculations, so I messed up here. And this is the experimental data, which is a little dangerous now. We are taking the derivative of this entropy with respect to temperature. But our data is sufficiently okay to at least show something funny happening here, down here, and that is really, I would say, first time I see something which looks like a lambda kind of transition, where the specific heat jumps up. Now, it's not as steep as you would like it from an incredible signal to noise, but at least it jumps up. So at high temperatures, you can essentially read off here the effective mass of the system with some caveats. It's not strongly renormalized. This Fermi liquid that we have above TC, it looks like a Fermi liquid, so it smells like it, so let's call it a Fermi liquid for now. It has an effective mass which is not much different, not a lot different from the non-effective.
How much is
Right. This would be 20% or so. 20%, but you're seeing it flows. It's not even clear how to define it.
I'm wondering if you
Actually, it's not even clear how to define it on the non-reflecting Fermi gas. Right? We know it should be 1, right? Because this slope here, there's a little wiggle here at low temperature. So even for the non-reflecting Fermi gas, only down here is your slope really giving you the effective mass which equals 1 for the non-reflecting Fermi gas. If you try to fit the line here, you accidentally get something very close to 1, but if you fit it here, down in this region, it's a little bit larger than 1. So it's actually dangerous to just compare the slopes at some finite temperature much higher than the Fermi temperature. On the order of the Fermi temperature. Okay, we can also get the compressibility, which deviates from the non-reactive Fermi gas more and more. That's actually expected for a Fermi liquid, but then at some temperature, it actually jumps up and does something funny again, indicating the superfluid transition. So here I now plot all kinds of markers for the superfluid transition. We have seen the heat capacity. We can independently get the condensate fraction, how much condensation is in this gas, using an old method that we have. That goes on as well, around 0.17, 0.16. The heat capacity has this jump pretty much at the same value. If I plot the entropy and compare it to the non-reflecting entropy and ask, when do I start seeing the deviation? This deviation for BCS theory should be linear in 1 minus T over Tc, so it should be a line. It looks like a line up here. Okay, down here something fishy is going on. Who knows what it is?
Isn't it basically starting to fluctuation, parent fluctuations?
I don't know. Maybe, yeah.
You expect. Maybe.
Could be, yeah.
It's a measurement and the other is theory. So.
Yeah.
Where is the theory?
So there is no theory. Theory is your fluctuation.
No, I'm just saying that you expect the entropy to start going down because of.
Yeah, okay. Which it does. Which is 1 minus the entropy here. Yeah. So yeah, I could be. I don't know. Okay, and so we can give some value for the critical temperature now that takes these measurements into account. We can debate on how to fit these things and get some idea, but I don't think it's far away from that value.
I would object because you see in terms of condensate fraction, you have a tail with positive second derivative, which theoretically would be very weird because we know the critical behavior which corresponds to the negative second derivative.
Careful, this is the condensate fraction of the total entire gas.
Yeah.
So it's actually integrated over the trap. Right? So,
but somehow you recalculate the whole thing into a homogeneous.
That's how you not this measurement. That's the only measurement that is not coming from a local measurement.
Oh.
The condensate fraction is just a global. We just expand our cloud and see how many guys are in the condensate peak, which is a global measurement. Trap average.
I see.
Yeah. Everything else is local, but this is not. Yeah, so all these guys show the onset. Well, this, for example, this point is also at 0.175. Yeah, I don't know whether it has any. Really, but you know.
Yeah, but once again, the critical behavior is characterized by known exponents.
Yeah.
So just you have to fit them properly just to avoid these finite size effects.
Known exponents, but unfortunately there is the question whether there is another phase, like this pseudogap story going on. So I'm not sure whether we are allowed to assume anything, right?
Of course, the best solution would be to do sort of finite size analysis, so that you change some parameters and see how everything evolves. Because you really want to claim something which corresponds to the thermodynamic limit rather than finite size.
Well, finite size, our cloud size are like hundreds of micron in size. The Fermi length is 1 micron. So, I'm not... like a million-ish, yeah.
Yeah, but million is just the whole system size, and the critical region is much, much smaller.
Sure.
We care only about the size of the critical.
Temperature. Yeah.
That's always.
Yeah.
And what temperature would correspond just to maximum of heat capacity and maximum of compressibility? If you just
Yeah,
if you take the maximum.
Yeah, the heat capacity has this heavy scatter because of the derivative of the entropy. I tried to smoothen it with this solid line. Take this guy, maybe 0.15 or so.
Yeah, that's what I would
but
say.
that's the maximum, and maybe
yes.
why not?
I would just claim a bigger arrow bar. This one in the brackets.
Okay,
It's
okay.
smaller maybe.
Okay. We can discuss that. That's
sure.
Yeah. I'm not, I don't depend on this error bar. 5 minutes. Awesome. Well, so also the critical entropy we then get, of course, but of course that error bar depends on that error bar. Okay, which is nice. So now you know how low you have to go in entropy before you get a superfluid with resonant interactions. Now I can quickly tell you this was all equilibrium measurements. This is too heavy a slide now. This is much easier to read. This was all equilibrium measurements. But now we do a fun experiment where we rip the spin-ups away from the spin-downs and let them smash into each other again, just to see what happens.
How do you do it?
So we can apply a Stein-Gerlach gradient to separate spin-ups from spin-downs. Now it's not as trivial as for electrons, where of course you really have opposite magnetic moments. In our case, the magnetic moments are very, very similar on resonance, which is sad, but not so similar away from resonance. So we go to low field, apply the gradient, and then jump back up to resonance after having separated the clouds.
But you have S-wave pairing.
Yes.
S-wave pairing. It means that if you separate this spin component, the character of the order transition should be strongly different.
So you're saying now it should be first order.
S-wave pairing, you pairing atoms with opposite spin, and you have no possibility to have this pairing.
Yeah. Now there's no pairing anymore.
Your characteristic cannot be used for this cloud.
What characteristic?
Because you see, in any cloud, you have only one direction speed. So S-wave pairing is
Gone.
ruled out.
Yes.
And you have different pairing.
Yeah, we have no pairing in these clouds now.
You have normal.
Yeah, it's just normal Fermi gas.
Okay, then.
It's a new part of my talk, for which I have 5 minutes.
But superfluid, because.
Yeah, well. So listen to that. These guys now move towards each other and might actually pair up again. And then you have a
but only
superfluid.
when they are united.
Yes. That's why it says from magnetism, which is this state, to superfluidity, which is when they're overlapped. Let me just give my talk. So this is how we do it. At low fields, we separate them because they have different magnetic moments. Then we jump up to the Feshbach resonance, where magnetic moments are very equal, so we cannot do this trick there. And then we take two images for the spin ups and the spin downs separately. Those are the two clouds. No superfluid in here. And we can, of course, construct a total density and a difference density, and color coding them red blue because it looks nice. Now we can try this first by jumping to the non-attracting regime. Here I show a movie of the density difference, and here that's encoding the density difference and the sum together. So you can look at both. It doesn't really matter. And you see how for no interactions these two clouds boringly just move through each other, right? As you would expect, there are no interactions going on. They just move through each other and change sides. But now if we switch on the strong interactions, This was the story of the non-interact. It looks very pretty, but it's actually boring. These clouds just penetrate through each other without any issue. If we do this on resonance, we see this dramatic repulsion of the clouds. So the reds encounter the blues and crash into them like cars in a car crash, and then they bounce back again. So it's two gases, each 1,000,000 times thinner than air, bouncing off each other. It's kind of shocking. We actually didn't know that this would happen. We had no idea. We thought maybe they immediately form pairs and become a superfluid, but no, actually they first repel, which is cute.
In terms of local Fermi energy, the maximum, how long is this amplitude?
1.
So essentially,
So we separated them by 1 cloud size, which means 1 Fermi energy.
So you and how much energy you have in collective? I mean,
well, so we try to start out.
If you measure that in units of the
Fermi
gas, yeah.
So we try to start out without any relative speed. So that means we have 2 clouds next to each other without relative speed, but they're separated by a distance which in energy space means 1 Fermi energy. So that gives you your average energy that we have in this collision. Once they pick up speed in the harmonic potential, they will gain energy of the order.
So basically, all this collision, even if the collective energy there, it's well above the condensation energy, right?
Yes, so we have a hard time actually later cooling down below TC in this business. We can cool. I will show you now in a second that the evolution afterwards is very, very slow, and during that time we can actually cool, but we have a hard time cooling below TC. We sometimes manage, but not often. This is the total density. You see how there is a striking interface that appears between spin ups and spin downs, really because they don't want to penetrate.
Yes, so I suggest that you maybe you can speak extra 5 minutes, but then we will have a question session at lunch. So because there are many questions.
I can actually.
Anyway.
Yeah, I can wrap up in a minute or so.
Take it up. So today is the only day when we have to observe time limits in the morning because of it's holiday. All the shops are closed. All the restaurants are closed, and so the Greek place told that they will be open only for us. So we have to be on time.
That's very nice.
So take your time, yeah.
Well, okay, I'll wrap up just to. You got the big picture. They bounce off each other, which is nice. They do that a couple of times, bouncing off each other, and then it still takes a very long time, over 1 second, for them to actually penetrate into each other and form pairs. Form pairs below TC. Hopefully, I don't know. At least completely overlap. And that is quite striking. I will spare you this slide. The very slow evolution in the end is due to spin drag. If you have 2 sets of particles, they scatter, and of course, the scattering results in a drag force, which is proportional to the average momentum change in the scattering event and how often it happens. Right? That's given by this spin drag coefficient, and we can get this coefficient from our data. I'll spare you this.
To that, you shouldn't get this kind of dissipative dynamics. Wouldn't predict any kind of oscillation like you see these.
That's right. So this
clearly
story is linear transport theory, which happens at the end. But this first bounce is not described by this because the bounces are complicated. You have a Boltzmann gas outside, which is not scattering at all, and in the center you have super high scattering. So I don't even know how to write down an equation. And wavingly, though, it's clear that it's easier for the particles to bounce back ballistically instead of diffusing through the spin-up cloud, which takes a long time. So that's why they bounce back.
Is there a temperature increase?
The temperature increases when they collide, but we also have the option of later lowering the depth of the optical trap to actually let out the hot guys again, do evaporative cooling, before then ramping up the trap again to study the evolution.
Yeah, so maybe isn't the diffusion coming because when you collide a few times, you heat the system up, both because of these collisions and because you create loss in the interface?
There's no loss here. No loss.
Well, you create, there is strong Everybody lost.
No,
Or it's not
You're
responsible.
thinking of the BEC side. This is on resonance.
Oh, this is on resonance.
Yeah.
Still, you can create molecules on resonance.
No. Pairs maybe, but
Pairs.
yeah. Pairs probably around
There is no
2C.
difference.
But
No, pairs are Cooper pairs.
Yeah, it's the same. And away from resonance, it's always Cooper pairs.
yeah, now that would happen very close to TC,
No, but
and still then they would not be lost, right? They would still be there.
Why not? Why not? You're in a highly non-equilibrium state. The system wants to create superfluid in the interface, so it relaxes. Keeps up.
Please. Let me just. Okay, this is a harder story, so let's not do that. Just to tell you how interesting this scattering is. The scattering is resonant, right? It's just given by the wavelength squared of the particle scattering, or 1 over the Fermi momentum squared here, because it's resonant. So that's nice. That means the mean free path is just given by 1 interparticle spacing. It's as short as possible. Sometimes people call it a perfect liquid. If you now calculate what should be the collision rate, how often these guys scatter, it is extreme. It's the Fermi energy divided by h bar. It's as fast as it gets. If you calculate the diffusion constant in this gas, turns out all the density dependent factors cancel and you get h bar over m as the diffusion constant in these gases. And that is very slow. It's 100 microns squared per second. And that's exactly the diffusion we observe. We have clouds that are on the order of 100 micron in size, and they take 1 second to fully penetrate each other. So that shows quantum limited diffusion at a diffusion constant given by h bar over m. We can also calculate the spin conductivity, how easy it is to move. It is very uneasy, it's very hard. It's actually the quantum limit of conductivity. In 2 dimensions, this would look like 1 over h bar. You would lose this kf factor there. And we know this from the quantum Hall effect or anything. There it would be e squared over h bar for charged particles. So we are seeing this quantum limited diffusion and conductivity. So that's my little theory, which I don't give. And that's also to be spared. Maybe the graph of the diffusion constant is interesting, where here we show at high temperatures we have a universal scaling. It goes, the diffusion constant, which we plot here, it goes like the temperature to the 3/2, which is simply coming from a scattering cross-section, which goes like 1 over the temperature, because it's resonant. It's not going like a scattering length square. It goes like 1 over the temperature on resonance. And the velocity, the average velocity, also goes like, well, it goes like the square root of the temperature. That gives you this t to the 3/2 behavior, which we see. We can also fit the coefficient, which is nice. But at low temperatures, it levels off, and we see a quantum limit of diffusion. At extremely low temperatures that we cannot reach, it should actually shoot up again. But no one really knows how it should go. There's a superfluid around, you know. You could think that it should be essentially phonons propagating then instead of free particles. So things get messy here. Unfortunately, in the experiment, things get messy as well, as you see from the error bars, because we have a hard time cooling below TC when we are doing this crashing experiment. I think with that, I spare you that we can get the spin susceptibility unless you ask about it. We get the spin susceptibility. Great. From this data, and I just conclude this part. We have very slow spin relaxation in this funny measurement. The best superfluid turns out to be the worst spin conductor. S-wave, that is not surprising, but it's cute. We observe the universal law at high temperatures, which is what you would predict on resonance, and then it saturates, the diffusion coefficient saturates to a universal value just given by h bar and the mass, which is very cute. We did measure the spin susceptibility, which I didn't show you, which shows the Curie law at high temperatures and the departure from compressibility at low temperatures as expected for a Fermi liquid. So in the range that we observe here, everything looks like a Fermi liquid, and we don't have the resolution to decide on pseudo gap or things like that.
High temperatures.
Yeah. Well, it's not. We sometimes reach at low temperatures, but you see with what error bars we do that. So
No, that it's still high.
not. Well, it's not super high.
No, that's 0.2, right?
It's 0.2, yeah, which doesn't show up on this slide. But this is 1. This is 0.2. It was pretty low.
Yeah.
And you see, this is the spin susceptibility, this is the compressibility,
I
the two.
thought it was in there.
Yeah, it's not. It's actually not nice here. Plotted, yeah.
So I'm trying to understand what you mean. All of these quantities, like spin, drag, spin
Yeah.
susceptibility, diffusion coefficient, are linear response coefficients.
Yeah.
Now, around the ground state, which is, say, Fermi gas at unitary, but you start with a system which is far, far from this ground state, because you have all spins up and all spins down, which is or it's very, very far from, I would say, the equilibrium state, not necessarily the ground state. Because, and I don't understand how can we extract linear response coefficients in this case?
So here is the region with the bounces, which is dramatic and cute and interesting. Here is where we extract the transfer coefficients after 1 second.
You say after it already equilibrated
Yes.
in a region of...
We have just an epsilon.
Interface region.
Yes, they're almost overlapped. There's just a little bit sticking out still. And this is 1 second, which is an incredibly long time scale for us. We can even cool in this time scale here.
And you do.
And we do. To vary the temperature before we start the experiment here.
But cooling is evaporative cooling from the fringes. Does it propagate all the way down to the center? Because if you evaporate from the fringes, then there is no collisions in the region where where the gas is spin polarized.
No, radially the clouds are already very, very well overlapped in the center of the jet. And you might be worried about the very outskirts here and here, but that's not where we measure the transport coefficients. We measure in the center of the jet.
So you say the system can be cooled during this transport?
Yeah. And we actually measure the temperature using our equation of state in this axial direction and check whether the temperature is locally equal everywhere. Granted, in the spin polarized wings, it might deviate, but in the central, third of the cloud where we check the temperature is equal, and that's where we take the measurement.
And at long times, it goes into an equilibrium state.
At very long times, it just overlapped again. Yeah.
I would
But it takes a long time. Like even after half a second, it still looks like that here.
I would like to ask about speed relaxation, because the fact that speed relaxation is low quite expected, because usual collisions do not lead to spin relaxation. It is a relativistically weak process. So what process is responsible for spin relaxation? It could be dipole-dipole interaction, increased or that. So usual collision do not lead to spin relaxation. If you write down a balance of equation, spin will be conserved.
A spin is because you're thinking about spin.
What mechanism is responsible for spin relaxation? Because usual collision are not enough.
I think we're talking about different things. You're thinking about we have all kinds of spin ups, and then after some collision, some of them become spin downs. That's what you're...
No, if one spin up, if other spin down...
We have just a couple of minutes.
Okay, we can discuss it. No, I didn't understand the mechanism of spin relaxation.
Spin currents are not conserved in a collision. Momentum currents are...
They should conserve if you have non-relativistic approximation.
No, they're not conserved.
We shall discuss it.
It's mixing between, it has a region where they have spin up and a region where it's spin down, and they mix. It's just mixing. How long the mixing takes. So there is a mixing layer that grows and grows. That is completely allowed. There is total spin conservation is completely obeyed, right? There is no...
Did you satisfy?
Yes, of course. It's just mixing. The total spin is SV equals 0, of course, in the beginning. Let's look at the SV component.
Okay, but then spin relaxation, it is too strong. Okay, we can discuss.
We have a couple of minutes, otherwise we risk to be left without lunch today.
Yeah.
This is a special day.
Yeah, I would say I'm happy, I'm done. Took too much time already.
Yeah, please take your time to finish that.
No, I was actually already at the conclusion with the... what was it? I spared you all this math, which is good. And then... that would be my conclusion slide, just telling you about the thermodynamics of superfluid transition, measuring the equation of state down to below TC, and the second was the spin transport, showing this universal spin diffusion h bar over m skewed. So in principle, every system like electrons and neutron stars and all, they should have this lowest diffusion at some finite temperature. The helium-3 seems to show that actually quite nicely. Electrons in high TC superconductors are not quite there, but not far off. H bar over m sets the scales. It's nice. Thanks.
Yep. Many questions during the talk, so we probably should know what's the right minutes.
I want to thank the organizers for giving me the opportunity to come to this conference and present this book. I want to also apologize to few people who saw large parts of this talk last summer in Dresden. So I will discuss about realization of exciton Bose liquid in bosonic model with ring exchanges, and from the start I want to acknowledge student working with me, Jan Hoktay, who did hard work in this project, and also many discussions with Matthew Fisher. So here is the outline of the talk. I will first put this work in a somewhat broader context where we are thinking about exotic Bose metal type phases, and then I will discuss review in more detail this special example, exciton Bose liquid, and will summarize earlier numerical studies. Then I will describe our search for realizing this phase in a concrete model, and in the last third of the talk I will discuss slave particle perspective on this phase, and actually some lessons for parton gauge theories from this perspective. So the broader context is thinking about Bose metal type phases. These are quantum many-body states of bosons, where bosons are neither condensed nor Mott insulating, but instead are in some gapless itinerant state, and hence the name metal. You might wonder if such phases can exist, and I think you have probably seen some examples already, but weren't thinking of them as Bose metals. So early in the week we heard that spin systems are morally Bose type systems, and gapless spin liquids in spin systems, which arise quite naturally when one uses slave particle approaches with fermionic particles, are actually examples of some examples of Bose metals. And we know that for in such slave particle approaches where description is in terms of some fractionalized particles plus some gauge field, and in the case when we have a gapped gauge field such as Z2 gauge field, such spin liquids with either Dirac nodes of partons or Fermi surfaces of partons exist. They are stable. They can be demonstrated in specific models. For example, exactly solvable Kitaev type models with gapless partons are realizations, somewhat different from the more familiar slave particle approaches, but nevertheless. Then in the case when the gauge field is U1, the situation is more difficult. If you have Dirac nodes of spin-ons, then in theory it's believed that these are stable phases, but we do not know concrete examples in models. And the most difficult situation is when we have a spin-on Fermi surface, and in this case there is still, the theory is still unsettled, and we do not have any control demonstrations in models. And now if you think about these slave particle approaches, there is nothing sacred about the spin models. One can use them also for boson models at some generic densities, and in these situations very generally one gets some kind of parton Fermi surfaces. And in this work we discussed one family of such Bose metal type phases using some particular slave particle approach. And this is the closest to the topic of this talk, which is okay, actually so here so one motivation for studying Bose metals for us is eventually to use them as building blocks for perhaps constructing strange metal type phases of electrons. Now, as far as spin Bose metal type phases are concerned, there are actually experimental systems which so far look like realizations of such gapless spin liquid states. So these are two organic materials which are essentially half-field electronic systems residing on triangular lattice. They are not insulators because of strong interactions, so there is no charge transport, but nevertheless in thermodynamics they look like metal. So spin susceptibility has Pauli-like behavior at the lowest temperature. And also, even though we have no electrical transport, we have large thermal transport, presumably due to this, due to some such gapless excitations. So now the precise topic of this talk is so-called exciton Bose liquid, which I want to present as a special kind of Bose metal type phase. And this was discovered about 9 years ago by Parmacanti, Balens, and Fischer, thinking about possible ground states of bosonic models with strong ring exchanges. So, so this is, here I wrote down some hardcore boson model, and this ring exchange term operates by hopping two bosons on the opposite corners of the square to the other two opposite corners. And this EBL phase was observed, was discovered by asking what is the phase of such model where we are trying to condense, where bosons are trying to condense in some sense. So, and asking what are spin wave excitations about such ground state. So to discuss spin wave theory, it's for qualitative discussion, it's convenient to use roto variables where e to I phi is creates a boson, and n is conjugate boson number variable. So this ring exchange term then becomes cosine of this phase combination in the pattern plus, creating a boson, minus, destroying a boson, plus, minus. And let's, spin wave theory is, in the spin wave theory we assume that we are going into some phase where we can ignore compactness of the phase fields and expand with cosine. Okay? And then when we do this, we get just some harmonic theory. So this is like a coupled harmonic oscillator theory, which we can then easily diagonalize by going to k-space. And this ring exchange term in k-space becomes sine kx over 2 sine ky over 2 squared.
May I ask a question?
Yes.
So this Hamiltonian, does it conserve charge modulo basically 2? So is there only pair hopping across chains or?
Actually, it will be on the next slide. It will be on the few next two more slides. It actually has special conservation laws that boson number is conserved on each row and on each column. On each column.
Between the you can just replace bosons with fermions, or nothing will change because there are never signs accumulate if they're only pairs.
Yeah, it's true, but then you need to ask what is the dynamics of this. Well, what is the phase that they will form?
So this is a two-dimensional model?
It's a two-dimensional square, so we will. I want to consider two-dimensional square.
And sort of like a half filling?
So it can be a generic density. I will first discuss half-field case.
And so when the ring exchange, so the bosons can move all the way, all around the lattice, or they just move on a single plaquette?
So here I just described the ring exchange around elementary square plaquette.
So in that, the first term, it moves, I guess, black dots into the yellow dots, but can you, along vertical lines?
Well, it's a pair hop, so it's not, there is no sense that, well, you can think of it as this hopped here, but I did not. Yeah. Okay. So here I just rewrote this spin wave Hamiltonian, and from this you can.
I didn't understand the answer to this question. What's the difference between fermions and bosons in this model?
Non-paired. You can so this particular model with just nearest neighbor ring exchange. I can actually also rewrite it in terms of local fermionic model with ring exchange.
So answer is no difference. Right?
No difference, but then just rewriting is not the answer for the yes. Yes.
But the fact that it moves around in ring exchange would be something bosons more likely do. Is that right? But the fact that they're correlated motions.
Well, why we are studying ring models, well, at the moment it's not trying to study any realistic system, it's more trying to explore what such models may do. In this context of, say, in liquid materials, they are actually located close to metal insulator transition, and in that context, there are large spin ring exchange. But here, this is more theoretical study.
Sorry, but can you mention the exact condition when these two models are exactly equivalent? The rotor model and the ring exchange model.
Which model?
The rotor model and the ring exchange.
Well, okay, so I wrote rotor model mainly to motivate doing spin wave theory instead of doing some, I don't know, Schwinger bosons or some. For qualitative purposes, rotor models or boson models are the same. Of course.
But usually I understand for the rotor model they require the number of particles per side is sufficiently big when you do the movement.
But that's if you want to connect quantitatively this model with this model. At this level, I just want qualitative picture of spin wave theory in such ring models. So from this spin wave theory, you can read, from this Hamiltonian, you can immediately read off the dispersion, and it has this form product sine kx over 2 sine ky over 2. And interesting thing about this dispersion is that it actually vanishes on the ky, on the kx axis and on the ky axis. So in this resembles somewhat situation of fermions in a metal, where we also have a surface of low energy excitations, except that here we have surface of low energy excitations in a bosonic system. And the origin of these gapless lines is quite simple. If you look at this ring Hamiltonian, this term is invariant if you add to the phase arbitrary function of x plus arbitrary function of y. And basically there is a independent U1 symmetry associated with each row and each column of the lattice, and that U1 symmetry is simply statement that on the ring moves the boson number is preserved in each row and in each column. Okay? So the vanishing of this spin wave dispersion is not so exotic. Well, what is actually, so the main achievement of this work is actually in answering the following question. Is it justified to, or is it ever justified to do such spin wave theory where we neglect the compactness of the phases? And to answer, here I wrote now Euclidean action corresponding to the spin wave theory. So that's this ring term, and this is the usual term in imaginary time path integral, and answering this, asking this question about importance of compactness of the angle is very difficult directly in this language, because it corresponds to studying topological defects in this phase phi, which are some non-local objects. However, it turns out it is possible to reformulate this problem using dual variables, and interestingly, the action in the dual variables looks qualitatively similar, except that the roles of this ring exchange and some effective repulsion are interchanged. But now in this dual formulation, allowing this non-local topological defects corresponds to some local cosine terms, and then one can use local field theory techniques to study the stability to such terms.
Question. And yes. If you perturb the theory so that this conservation, exact conservation law is gone, will you change everything all of a sudden, or the system will be stable? Because you were using this conservation, special conservation.
Okay, so the original proposal here was that you can get a regime where in which where this would be stable phase also in the presence of hopping. And as a matter of principle, it is possible. It's probably not possible in the simplest field. One needs, but as a matter of principle, it is possible to find that these local cosines are irrelevant, and boson hopping, which is local cosine in the phi fields, is irrelevant. But yes.
That's what you're saying. You're asking the question whether the both liquid in the spin wave theory is stable, but in the spin wave theory, don't you have long range order really?
So here you do not, because of these special conservation laws, you do not have long range order. It's the precise definition of spin wave theory is what is the phase where you can neglect the compactness of the phase field.
But if you go ahead and compute spin correlations, they decay like power laws?
In this precise theory, correlations of the phase are...
What you wrote down before.
So if you actually, if boson correlation is ultra short range, because boson by itself cannot hold.
And the pair correlation?
So acid boson, like particle hole boson correlation has power law.
Power law.
Yes.
So it's like 1D because you have these lines make it 1D.
There is some quasi one-dimensional aspect in this, but it's not 1D. There are also some two-dimensional aspects.
Please, sorry, another question. So you mentioned this compactness thing, but this action that you've written, it's already, so it's gone basically.
So here it's gone. If you want to have a faithful representation allowing the cosine, you need to allow topological defects.
And you just put them by hand and calculate energy of those?
It turns out that in dual theory, allowing topological defects is like allowing in this, starting with Gaussian theory and allowing some local cosines in this dual field. And then you can ask whether, if this is your fixed point theory, you can ask with respect to that fixed point theory, are these guys relevant or irrelevant if we are small?
But so then relevance and relevance of this term depends on values of k. So they can identify range of k and u.
Yes, yes. So it's actually next slide. EBL, this phase where you can neglect the these topological defects, is stable for sufficiently large k parameter with effective k over some effective u, and at half filling this in that particular model, this ratio should be larger than something like 0.14. At generic density, certain umklapp processes or certain some of these topological defects are not allowed, and generically the phase is more stable. You need smaller k to stabilize it. And one signature of the compressibility of one signature of this EBL phase that I want to mention, since it is very useful in a numerical study, is density structure factor, and one can calculate it in this harmonic theory and obtains this form, product of sine kx over 2 sine ky over 2 times the prefactor, which is related to this stiffness parameter. And this structure factor, at any, say, fixed ky, this structure factor has a V-shaped singularity as you go across kx equal to 0, and this V shape opens up as you approach the origin. So now let me mention previous numerical studies. So as I already said, it was hoped that such EBL phase may be stable in more general models, not just with ring exchanges, but also with boson hopping. So that's the model which was studied, and this is the phase diagram at Hall filling, and for small ring exchange it's dominated by hopping and the system is in the superfluid phase. And then what was found that as one increases the ring exchange, at some point the system undergoes a transition to columnar valence bond solid, and as one increases the ring exchanges even further, particularly going to large K, where the model basically approaches just pure ring model, what was found is that the ground state has this pi CDW, and there is intuitive picture why this happens. This happens by some kind of kinetic stabilization. This CDW state is very hoppable. Each ring term around each plaquette can operate in this CDW state, and numerically exact quantum Monte Carlo studies find that indeed the ground state has this order. Now, the same model was studied away from Hall filling, and what was so this horizontal axis is exactly the phase diagram I had on the previous slide, and what was found that the moment one went away from Hall filling, the system became superfluid, and when one went to still lower densities, actually the bosons phase separated, and again there is simple intuitive understanding that this ring terms that I wrote down, they can operate only if bosons are next to each other, and they can be viewed as some kind of attraction between bosons. And then if you go to dilute boson particle density, when you have some attraction, it's very natural for bosons to clump together and phase separate. Yes.
Question. So somehow I'm afraid. So I would either expect phase separation. So suppose we are in the BBS or any state with broken translational symmetry density wave, and we dope the system, go away from half filling. I would expect that once you dope the system, we have only two possibilities. Either it's a super solid, so that there is no phase separation, but the symmetry remains broken. Because you see, it's a kind of, you add one particle or two particles, and all of a sudden your broken translational symmetry is gone. Your state is superfluid. It's a kind of strange.
Well, so here my understanding is
it's I'm talking of
here.
Infinitesimally small doping, like I don't know, very tiny fraction of particles or holes on top of half-filled situation. So in my opinion, this phase diagram is not realistic, because somehow it's either should be a super solid, and you have both superfluidity created by the condensation of particles or holes depending on the direction from half-filling, or it should be phase separation right away. Because you see, it's very strange. What you are saying is that you do an infinitesimally small doping, and your order is gone. I'm talking of the broken translation symmetry. It's unbelievable. Or am I missing something?
So yeah, you add...
Well, I know, so this is phase diagram from this group, and they studied it at fixed boson number. I know that under Sandvik and Roger Melko studied it as a function of chemical potential, and what they found is that there is a first order phase transition, and then there is, it's not staying at half filling, the density is slightly changed in that phase. But then in this superfluid phase, I don't remember them discussing
just keep it in mind that, in my opinion, this phase diagram is impossible. We can discuss it later. In my opinion, it's just impossible to have such a phase.
Well, so as I said, as a function of chemical potential, actually they go from this half-filled system to some density slightly away from half-filling via first-order phase transition.
That's
yes.
what I would expect here.
Yes. Well, okay.
Meaning that the cluster should go just to this line. Okay, but
no. It's not phase. But there is a uniform leak superfluid liquid only at lower densities. There is a cluster.
If your control parameter is chemical potential and density jumps, it just means phase separation. If you work in the canonical.
But no. But so they go from one of these gapped phases into a uniform superfluid phase, and then over some range of densities. And then eventually there is another transition.
Then just bring back to my comment. If you add an infinitesimally small density of carriers, your order is not supposed to disappear right away. It's like you destroy... Maybe this... so in under Sandvik's work, they undergo a transition from half-filling to density, which is some finite amount away, but not very large amount away. Yeah, but finite, right?
Finite amount.
Meaning that it's a first order phase transition.
Yes.
That's my comment. Was my comment.
What is cluster? I'm sorry.
So here it's a phase separation into empty space and boson-rich space. Okay, so we want to, so this simplest boson ring model did not realize the ideal phase, and we wanted to search for such phase, and we are not as ambitious. Here we do not try to find realization that is stable to both, to also boson hopping. We just focus on ring-only models, so these special conservation laws will be present, but then we considered a minimal modification of the model where we added, besides this one ring exchanges on elementary plaquettes, we also added ring exchanges on 2x1 and 1x2 plaquettes. And the idea was that actually this two types of ring exchanges will compete with each other. So while the CDW state is liked by this elementary 1x1 ring exchanges, it's not liked by these larger ring exchanges because they are completely inoperative in this state. So we hope that by adding K2 we will suppress the CDW and stabilize the liquid state.
So the EBL phase is along with the post separation?
Yes.
Okay, that's
Yeah. So actually what we found when we studied this model numerically is that yes, at half filling so this is the schematic phase diagram. At half filling we found that the CDW phase is indeed suppressed rather quickly by moderate K2, but the system went instead the system developed valence bond solid of the similar columnar type that was discovered in the JK model. And only at much larger K2 we tentatively realized the BL phase at half filling. But now the numerical technique which we use is a version of quantum Monte Carlo. This model which we studied has for positive K1 and K2 doesn't have sign problem, so it can be studied by quantum Monte Carlo, and we used the Green's function Monte Carlo, which is a version of a projective Monte Carlo technique. We start with some trial wave function, which in the context of ring exchanges we know how to construct quite reasonable initial trial states, and then we act on this wave function many times with the Hamiltonian, and this filters out excited states, and only the true ground state remains. And then in the true ground state we measure quantities that we use to characterize the state. So we measure density structure factor, which is just Fourier transform of the density correlate, and we measure plaquette structure factor. And these are the results for small to intermediate K2, from which I deduced the phase diagram I mentioned earlier. So on the left panel is density structure factor at wave vector pi pi, where we expect CDW order. And here you can see that for small K2, this structure factor increases with increasing system size from 6 to 12. It's a square 6 cross 6 to 12 cross 12. And this increases like increase of the Bragg peak with volume. And if we divide by volume, this quantity is then like a square of the CDW order parameter, and we see that there is non-zero CDW order parameter for K2 up to about 0.2, 0.3 over here, and then for larger K2 the CDW order parameter vanishes. And right-hand side is similar analysis of the plaquette structure factor at wave vector pi 0, which is where we expect this columnar type order. And here for small K2 we do not have this order parameter vanishes, and then for K2 larger than 0.3 or so, this order we have finite order parameters, so we have this dimer state. Now, as we increase K2 to larger values, at some point we actually also lose this Bragg peak in the plaquette, in this plaquette correlator, and tentatively, starting from about value 4 or 5, we do not observe any order, and we conclude that the system is in liquid phase. So this is a demonstration of one point in this tentative liquid phase, where now I show density structure factor in the full Brillouin zone, and you can see there are no features, no Bragg peaks at some hidden wave vectors, and you can see this shape with this singularity lines in the density structure factor here. And here we have plaquette structure factor in the full Brillouin zone. Again, no, we do not see any features other than this pi 0 or 0 pi, which I discussed finite size behavior, system size behavior before. So there may be something eventually happening here, but on our system sizes, this peak is essentially system independent. So it's quite reasonable to conclude that we do not have any of these orders. So now this is somewhat technical slide which I will skip. Now we studied this model also away from half filling, and here we are much more confident that we realized this EBL phase already for much smaller values of K2, starting from around 0.5 and so on. We just do not see the bosons are in some very uniform state with no features in any structure factors that we measured, other than this expected lines of singularities in the density structure factors on these two axes. And when we go to much lower density, we in this model also the system eventually phase separates.
What about pair correlations, off-diagonal pair correlations?
We have not measured this. It would be interesting to do it. We have not.
Is it possible that it's a pair that they have long range order?
Well, they are expected to have power law correlation. I don't think they can have long range order.
What prohibits them from having long range?
These special conservation laws.
Okay.
So now let me switch gears somewhat and present this part-on gauge perspective on the EBL, and motivation here is that really trying to learn something about slave particle approaches which are popular for constructing gapless spin liquids, but which lead to these strongly coupled gauge theories which are very difficult to treat controllably. And I already mentioned these examples like spin liquid with spin on Fermi surface. And in this particular context, let me also mention that one popular approximate way people discuss going beyond mean field is to consider trial wave functions obtained by Gutzwiller projection. And sometimes people say that this Gutzwiller projection actually is able to capture gauge fluctuations, and I want to say that actually this is not a true statement. The wave function is not the full theory, and the particular part on slave particle construction which I will discuss is also related to this to our work on this D-wave correlated Bose metal, and I want to argue here that EBL can be viewed as a as a special solvable example of part-on gauge theory with gapless partons and gapless gauge field. So here is so the context. Let's think in the context of some such ring Hamiltonians with maybe more extended ring terms, where we are deep in this EBL phase, and let's try to understand if we can recover the EBL phase from slave particle approach. The specific representation which I will take is where the boson is written in, original microscopic boson is written in terms of two partons, B1 and B2. So the Hilbert space, one boson corresponds to, presence of the bosons corresponds to N1 and N2 both equal to 1, and absence of the bosons corresponds to N1 and N2 both equal to 0. So the physical Hilbert space is recovered by this constraint. And now let me impart some dynamics to these partons but the natural dynamics in these cases where B1s move only in the x direction and B2s move only in the y direction. And it's natural because in this way the individual boson cannot move, but the two bosons can perform ring exchange motion by exchanging these partons like this. Okay? And I can also give a mean field type justification that this ring terms have large negative energy in such mean field. So when going beyond mean field, we know in slave particle theories we get gauge theories. There is also an emergent low energy field which looks like a gauge field. And there are different ways of deriving this. So here, let me justify this by starting with some formal lattice U1 gauge theory. So here, this is a model where I have two species of particles, B1 and B2, and some gauge field residing on the lengths of the lattice. And these two species carry opposite gauge charge with respect to this gauge field. So now one species hops only in the x direction, is coupled to Ex with plus charge. The other species hops only in the y direction and is coupled to Ay with minus charge. There is some dynamics for this gauge field. Here some cosine of Maxwell-like term and some E² term. And then there is a Gauss's law, divergence E is total charge, which is N1 minus N2. Okay? And if you take this compact lattice gauge theory and if you consider it in the strong coupling limit where electrical field does not fluctuate, you see that this Gauss's law will enforce the constraint N1 equal to N2, and we get back the original bosonic type model. And if you then ask what is the allowed dynamics generated in this sector, and starting from such system, you can only generate ring terms for this composite bosons. So qualitatively, this U1 gauge theory and the ring term, the ring Hamiltonian, contain the same physics, and I expect it to contain the same phases. So now, what is nice about this special gauge theory is that actually we can analyze it fully, unlike the cases with more generic Fermi surfaces. And here, this is possible because of the one-dimensional character of these partons. And we can use bosonization to describe, we can use bosonization approach. So, for example, this second line here, so in the absence of the gauge field, this is just harmonic liquid description for some Latinger liquid of partons moving in the x direction. And here I have, I used the description which contains both phi variables and dual theta variables. The boson number is del x theta over pi, so this is some short-range repulsion among bosons, which in the bosonization is actually a quadratic term.
Why don't you have king terms?
At this level, so again I ask, we have this compact gauge theory. I ask about a phase where we can neglect the compactness of the gauge field and the compactness of the phases. And then I will argue that this is actually equivalent to EBL, and the stability analysis is actually equivalent to EBL.
What do you have anisotropic gauges, some sort of pockets or something?
Well, so if I'm studying ring model, you see if I allow B1 to hop in partons to hop in both directions, when I allow bosons to hop in all directions. with this setting where one parton moves only in one direction and the other parton moves only in the other direction is very natural for ring models. Because when individual boson cannot hop, because say if you try to hop it here, the red guy cannot hop. But then pair of bosons can hop by exchanging partons. So when adding gauge field is just replacing this grad x phi by grad x phi minus ax. So this is partons moving in the x direction coupled to the gauge field. Similar, this red line is partons moving in the y direction coupled to a y gauge field with opposite gauge charge. There is Maxwell term. Commonly, when one treats such gauge theories, one treats the Gauss's law by introducing a temporal gauge field. In principle, I can do this here as well, but actually here I can just treat the constraint explicitly. So this constraint n1 equal n2 is del x theta 1, which is boson B1 parton density is equal to del y theta 2. And you see what is nice in this theory is that it's quadratic in all fields, phi 1, theta 1, phi 2, theta 2, ax, ay, and this constraint is just a linear constraint. So this is a completely Gaussian theory, and I can do any calculation I want in this theory. And I can also argue very directly equivalence of this theory to the EBL theory. So if I can solve this constraint del x theta 1 equal to del y theta 2 by introducing new field, this var theta field. Theta 1 is del y var theta, theta 2 is del x var theta. So when the boson number is del x del y this var theta, and I can integrate out fields phi 1, phi 2, ax, ay, and write action in terms of just this var theta field. This is an exact rewrite of this theory, and if you neglect this term which has more derivatives than other terms here, it's the same as the dual EBL theory by Parmahanti et al. Okay? And I want to make a few remarks here. So first, even though these manipulations are very simple, there is no sense in which these partons are free particles. Partons are very strongly coupled in this theory. The ultimate description is this EBL-like. The ultimate simple description is in terms of this var theta field, which is equivalent to EBL. And I also want to emphasize that this is not a EBL, this is not a sliding or cross-sliding Luttinger liquid. That's answering your question. So for example, if you calculate specific heat in this phase, it has T log T behavior, which is different from linear T behavior expected in the sliding or cross-sliding Luttinger liquid. So now one can I should say that this perspective does not really add to the EBL theory, in that all calculations in the end should be done in this EBL theory. If you are familiar with one-dimensional systems and thinking about quasi-1D, like coupled chains and so on, then you can actually use this perspective to very quickly recover some non-trivial statements in that original paper and even fix some problems in that paper. Like you can you can find expressions for interesting observables in terms of your continuum field. You find expressions for important residual interactions, but then studying the stability is the same as here. So now I want to mostly present this as a way to learn something about such parton gauge theories where both partons and gauge fields are complex, are gapless. So, for example, I can address this question: is Gutzwiller projected wave function able to capture gauge fluctuations? And I think it cannot. If you think how these wave functions are constructed, you write mean field in the absence of any gauge field, and then all you do is just perform Gutzwiller projection into the correct Hilbert space, impose the constraint. There is no way in that construction where you introduce gauge field fluctuations. And here you can actually very explicitly see this. What happens to this theory if you just do not have gauge fluctuations but have only the constraint. Okay? Again, this, so just drop all.
Maybe I don't understand. So something the gauge field is basically just a way to implement it. It was introduced as a way to implement the constraints. It gains some dynamics at low energy, so maybe that dynamics you cannot take into account. But if you implement the constraint in another way, in a sense, it's
just implementing the constraint is not the same as introducing spatial gauge fluctuations.
That's right. So it's like taking the gauge field at infinite coupling, right? Or
no,
because the Maxwell term is not there.
Lagrange multiplier.
Yeah, it's like a Lagrange multiplier.
Well, when you derive from slave particles gauge field, the spatial gauge field arises from some Hubbard-Stratonovich, from phases of some Hubbard-Stratonovich field. It's not just the Lagrange multiplier. And I claim that Gutzwiller projection just doesn't have that. And here you can, so if you take this theory and drop the gauge fields everywhere, you can still analyze it, and you get some harmonic theory for it, but now instead of where we had termed del tau var theta squared, you have del tau gradient var theta squared, and this theory is qualitatively different from the long wavelength EBL theory. It's actually more close to cross-sliding or sliding Lagrange liquid, in particular the specific heat is just linear heat. And one can demonstrate this failure of Gutzwiller wave function to capture correctly long wavelength properties of this phase very directly by working with wave function. So let me just from this slide, let me just say the punchline, but actually in this particular example, all long wavelength properties which you calculate with the Gutzwiller wave function are the same as in the mean field. So it does not even change any exponents. And besides that, it's qualitatively wrong at long distance. And I suspect that the same applies to all gapless spin liquid wave functions obtained by just Gutzwiller projection. And it's interesting, would be interesting if one can learn how to incorporate these gauge fluctuations in the wave function. So this is a summary of the talk. We realized EBL in a concrete hardcore boson model, and I discussed interesting perspective on EBL, where which can be as a solvable parton gauge theory with gapless partons in gauge field, and some lessons about such gauge theories and wave functions. Thank you.
Questions, if there are any.
So we actually had a sample with this stuff in it, and try to look at transport. How would it be different from regular metal, besides changes in specific heat or?
So this particular model would not have any electrical transport.
No. Okay.
Because bosons, there is this special conservation law. But for example, it will have metal-like heat transport.
I see.
It's not
Yeah.
an insulate.
Yeah, yeah.
So let's, if there are no more questions, let's take very short coffee break of just 5 minutes. And then
most of the people cited it for the model itself.
No, so actually I worked with Asia last year, organizing this. He was your student, Oh, I mean, yeah, so actually, the moment actually
First place I was so anything about it. Second they have to solve this. But I have to teach.
actually,
Oh yeah, look, I'm not involved I'm involved in my office in this sense I'm involved. But other than this, I've heard of them. My friends have
I kept essentially 1 week to teach my spring break. Very big unit.
Если там они сильно подставили, смотри, насчет технически там спасать, можно позориться, всякие там ложи, меч, едов, палки там, да, то же самое. Там,
Странно, что они
So I didn't really register I was wondering to check my way.
Try to find a yardom. Let's see. Because international starts.
You should, yeah. Great. Oh, that thing's I fill that out. Is that how you I'll send this to someone. Thanks.
вроде программы есть.
Есть две шкалы вариации полностью не существует в природе. А вот мы сейчас думали, вообще мне не показал, не существует две шкалы, все. Там не показал. Ну, они, может, не поссорились с синтаксисом Щеркова, но не поссорились с Алисой. А, очень похоже. Просто добавляют на большинство.
Сколько у нас в институте есть отдельные системы, которые системно
Ну, все. Видишь, что то есть это объясняет. Лучше мероприятие. Все объясняет.
Let's start lunch today. Let's start. So, Егор, на самом деле, у него до и после почему бы нет? Более попробуем. Волнуется желать, я думаю, очень все равно.
Я, кстати говоря, сейчас собираюсь это самое спросить аудиторию, а что они, собственно, сами хотят? Они хотят слушать про это или хотят слушать про птиц? Потому что ответ ясен. Хорошо, не бойся.
Борис, так как будет на другую тему? А?
Ну, организаторы не хотят.
Нет, ну то есть, я не спрашиваю отношения, я спрашиваю что. Так как на другую тему?
Почему? На другую, чем что?
А у тебя был...
Да они хотят два. Не-не-не. Да тоже. А, слушай, а там другое название? Что? Ну, слушай, то же самое.
То же самое?
То же самое. Да, я просто не смотрел, когда я писал.
А, я понял. Ну вот это учишь.
Да.
Да ладно, это простите. То есть не доклад поменялся, а название поменялось. Вот я хотел выяснить.
Это уберу, так что никто не видит.
Чего, да ладно,
Спасибо, что рассказал.
аналогию не очевидно. Аналогию не очевидно.
They're consistently the other thing is, I think it's not allowed for bigger purposes. What? Well, the unit kind of gas. And then this one.
So our policy this conference is that regular scientists give one talk, but the most outstanding scientists like Boris give 2 talks.
Wow.
So he will give talk before lunch and after lunch.
Okay. What introduction?
I suppose.
So thanks for inviting me. So it's an overview talk. I apologize. I actually it's the same topic but a little bit different title. So we was thinking about this subject for a long time. When I thought about what would be the purpose of this review, I think we have done everything which we could in this area. And we don't see how to proceed further, so we need some friends from the numerical side to help us. We think that very big questions remain about very simple systems. Helium-3 is one of them. You might think that everything is known about helium-3. I think that almost nothing is known about helium-3 in certain interval temperatures, very simple. What is conventional temperatures between 0.3 degrees and 20 degrees. As an example, mostly, I will mention it at the end of my talk, but mostly I will speak about either electronic or bosonic system with interactions, which is colon interaction, dipolar interaction, or anything in between in 2 dimensions. So let me start. So I will have in mind simple dispersion law, E squared over 2m, nothing fancy. Translation invariant system. An interaction will fall like 1 over distance between directions to some power. I will have in mind power between between 3 and 1, between the polar interaction and the polar interaction, and anything in between. So what do we know about it? We know 2 limiting cases. Potential energy scales with density inside, proportional to density in 2 dimensions. Kinetic energy, potential energy also scales somehow with the distance between electrons. This is density, which is 1 over r squared, and g is this power. So if you divide one by another, you see that j equals to 2 is a critical value. So which distribution between electrons and, for example, helium-3, which where interaction is 1 over r to the power 6 in large distances, And the difference is that at large densities, electrons are liquid, and at low density, electrons form in a crystal, whereas in helium-3, it's just opposite. At large density, it is a crystal, at low density, it's liquid. But other than this, what they have in common is that there is a quantum phase transition between crystal and liquid.
Is it all in 2 dimensions?
Huh?
It's in 2 dimensions?
No, I'm saying that in 3 dimensions, as an example, there is a transition in 2 dimensions, actually it is in 8 dimensions.
But then wouldn't kinetic energy go then to 3 times?
Yes, yeah, sure, but the fact will remain that at large densities, in Coulomb case, electron system is weakly interacting. At low density, it's, this is example of 2 dimensions, yes. But the statement is genuine about this.
But not in 1 dimension.
Not in 1 dimension. No, not in 1 dimension. I'm not going to speak about 1 dimension, it's special. But anything above 1. Okay, now, what do we know about the transition between crystal and liquid in general? It has a long history, and Landau mentioned that all crystal liquid transition should be first order because qubit invariant for the parameter could be constructed. It was a mean field statement. Then there was exception for this rule, which was addressed by Brazovsky, but at the moment it is almost a theorem that all transitions between crystal and liquid, direct transition between crystal and liquid should be first order. So there are no exceptions from the rule, no counterexamples. As far as I know,
2D
melting.
2D melting. 2D melting.
It is not a direct transition. Direct transition between crystal and liquid. If there is intermediate phase, it's different. I'm speaking about direct transition.
But
So
quantum,
melting is not a direct transition between crystal and liquid. There is
You
a
need
pneumatic
a
phase.
genuine
and
long-range order,
Huh?
right? You need a genuine long-range order. Because in
no,
2D and 5D,
no, but
There's an ecstatic order.
there is an intermediate phase in between of crystal and liquid, which is hexatic order. And I'm speaking about direct transition. So transition between 2 phases. So that's a theory. Now, if there is another sequence of transitions, it's a different story. So
But this is on a continuum, not on a lattice or something.
no, it's a translation invariant system. So I'm speaking about translation invariant system. Now, there is another statement. So this is correct for kind of for 2 and 3 dimensions, and also it does depend on interactions. So whatever interaction is, that's correct. For example, we don't know any crystals which melt as a second order phase transition in 3 dimensions, regardless of interaction. Now there is another statement, which is more subtle, that in 2 dimensions, and if interaction is anything in between Coulomb interaction and interpolar interaction, between 1 over R and 1 over R, first order phase transitions are also forbidden. So then, which tells you that there is something in between, so there are intermediate phases. Now, for dipolar interactions, the statement was known, it was formulated like directly, but was known for in the case of spin systems. In Coulomb interaction, I think that we will Steve proved it. It is actually very simple proof. Relatively simple proof.
It's that very unique for dipole and Coulomb. What about like?
No, anything in between.
Anything in between.
Yeah, including these 2.
how do you conclude that the phases are necessarily quantum? Because
Sorry?
the 2 above statements, they're just the statements.
If you look, I mean that these are 2 statements. One is kind of it doesn't have a status of the theorem, but it is very strong.
I
mean that there are a lot of, I don't want to go into this because my goal is to go through
my question is very simple.
but there is very serious arguments behind this.
I know the argument. My question about the third line, when you say quantum.
This is also not a theorem, this is what our conclusion is. If you think that there is another resolution of this paradox, we would like to know.
Just a question, why quantum not
why classical?
Why not classical?
Sorry?
Why not classical?
Why not classical? What's wrong with classical?
What does that
Oh,
mean?
it's at zero temperature. Yeah, you can, in classical,
Why can't you get a microemulsion for a
Exactly,
classical
it's
system?
classical, I believe.
at final temperature? Yeah, sure. You should. In classical system, you also should have such a question. But I'm going to speak about zero temperature. Oh, you're addressing this quantum. Yeah, you can drop it.
All of a sudden, you put this word quantum, and I just.
My apology. So, I will speak about zero temperature. But yes, in classical, for example, if you consider another system, lipid films on the surface of water, which has strong first-order phase transition and dipolar interaction on large distances, you will have the same problem with the same, difficulties with intermediate phases. How many we can discuss.
So if you suppose you have an interaction which can be decomposed into a constant, like a contact interaction plus a cool.
That's exactly what the lipid films have on the surface of water. And all above it is above realized. Okay, but I'm not going to speak about this classical system. I'm going to speak about either electrons. So what are objects which I'm going to speak about? Either it's two-dimensional electrons, or it is a Bose gas with dipolar interaction. Either it's a magnetic dipolar interaction, or there are atoms which large polarizability, apply electric field, you have dipoles and dipoles in two dimensions interact. You can think about, okay, so in certain density it's a crystal, in other density it's a Bose liquid. How do you go between these two phases? The same problem. Okay, now about electrons. So there are two realizations. One is MOSFET, most successful device of 20th century, and another is quantum well. Now about MOSFETs. So why don't you just don't touch my computer, break your computer, take MOSFET from there, make experiments. What's wrong with this? It's very good MOSFET. Answer is the following, that in MOSFET there is a two-dimensional thin gas in a gate, which is metallic gate, so electrons on large distances interact via dipolar interaction because of image charges, and at small distances they interact via Coulomb interaction. So as a function of density you change this power. So what will happen is that at a given distance to the gate d, when density is very large, distance between electrons is small, so they interact via Coulomb interaction. So at large densities they are liquid. At small density, when distance between electrons is larger than distance to the gate, they in different paradigms, so to speak. In paradigm of helium-3, interaction is dipolar. So at small densities, they again are liquid, weakly interacting liquid. So that's what illustrates in this diagram, that here and there, they are liquids. So as you change density, what is essential for what I'm going to speak about, that they kind of go to regular crystal. Now, at which RS, at which the ratio between potential and kinetic energy this transition occurs. It's not very well known, but it is clear that this RS is critical, RS is big. So best estimate is 38 after Zipperley. I will criticize this number later on, but let's take it as a rough estimate. So it gives us distance to the gate at which anything could happen in principle as a function of density. Anything interesting? About 1,000 angstroms. So this is a kind of last century MOSFET. It is a MOSFET in which industry was interested 40 years ago or 35 years ago. Now if you break your computer, the distance to the gate will be 30 angstroms. Now, what's wrong with that MOSFETs? Take them, but they had bad mobility. So you also need low density, strong correlation. So this combination makes it difficult, and there are very few objects. But anyway, I'm going to speak about this region. There are some experiments in this region, but I just want to explain what's the experimental problem, why there are not that many experimentalists who are able to operate. So you have to go to some place and convince people to make MOSFET with the distance to the gate 1,000 angstroms. Intel is not interested. They will tell you, are you crazy?
What is the symmetry of this intermediate phase? Is it gexatic?
No,
what symmetry is broken?
I will tell you later. So as I said, I would like to make it very simple. So let me start with dipolar interaction. Suppose there is a dipolar interaction between electrons. So dipolar interaction is like a capacitor. So capacitance of the capacitor is 1/d, distance between plates, and this is capacitance per unit area. So if there is a first order phase transition, and there is a capacitance which is independent of the density, which is independent of the area, you have to include capacitance energy into the total energy, and then if there is a first order phase transition, there is a phase separation, you can find fraction of the phase using Maxwell construction. So suppose we did it, and we have fraction of minority phase. Then the question is, what is the shape of this phase? So usually the shape is done by minimization of surface energy. So, and usually it's positive. So if it's azeotropic, it's sphere. Okay. Now, let me come back to, so that you can understand almost everything which I'm going to speak about if you know formula for capacitance of a capacitor. So this is again, I forgot to apply here. So this is area, this is capacitance, area divided by distance. This is Kirchhoff correction to capacitance due to fringe field. So it's proportional to radius of the capacitance, not to capacitor, not to area. R is the radius. And times logarithm of R over D. So this term is smaller than that one. So first term gives you contribution to the area, to the bulk energy. Now if you expand total energy, which is total charge square divided by capacitance of a capacitor, with respect to this term, you will find out that there is a bulk energy, which was already included into Maxwell construction, minus something like R logarithm R. So this minus is important in terms of course times the density of electrons squared. So this can be interpreted as a surface energy, energy associated with the surface. So this term is universal in the sense that it's independent of the shape, only on the area. This term is not universal. This is negative, and it's R logarithm R, whereas surface energy associated with short range interaction is just proportional to the length of the surface. So when you sum up these two, you find out that at large areas of minority phase, surface energy is negative. So it's useful to break this bubble by 2, and then another bubble by 2, so that's how you get microemulsions. Now, it's a mathematical tool which you have to develop. So instead of this Kirchhoff formula, in principle, you have to write energy, surface energy, at arbitrary shape of minority phase, not necessarily single connected. So you can write arbitrary bubbles, system of arbitrary bubbles which are may or may not be connected, and calculate energy and compare them. This is this formula represents this mathematical tool for this. This formula, this is microscopic surface energy, which depends on angle. And this is integral dl, so this is a kind of bubble of minority phase. dl is element of the of the surface, and this integral is L logarithm L, roughly speaking, where L is its characteristic size. This formula is correct. It's actually a very beautiful formula, in my opinion. It is correct for arbitrary distribution of bubbles with arbitrary shape, arbitrary numbers, connected or not. So draw me any geometry. This is energy, surface energy. This formula for dipolar interaction was derived before us, long before us, in the context of two-dimensional ferromagnets with dipolar interaction. For any, interestingly enough, for any other interaction, this formula is also in between of dipolar and Coulomb interaction, including these two. This formula is also correct, and we derived it for Coulomb interaction and for anything in between. And it is much more difficult to derive than for dipolar interaction. But it is not my goal to go into the details. I will just use it. So you cannot, for dipolar case, it is first step is quite simple. So I know area of minority phase. So I have to compare different distributions of this minority phase. So there are two possibilities. One is I can have stripes of two different phases. When fraction of minority phase is 50%, which is not minority, then there is no other possibility but to have stripes. It's a symmetry question. When minority phase has a smaller fraction, much small fraction, it is also, then it is tricky. You can think about two possibilities. One is just stripes. By the way, I forgot to mention that some of these two terms gives you a scale, characteristic scale. When, say, when negative contribution wins. So this scale will be exponential in gamma. Gamma is microscopic surface tension. So there are two possibilities. One is you can form bubbles at this point where minority phase has zero or small fraction. You can drop it by bubbles and put them far away with this particular radius, or you can form stripes or just rivers, say a river of liquid floating in the crystal, and then the distance between them goes to infinity as you approach this critical point. So the difference between these two states is just numeric. So it depends, now competition between them depends on anisotropy of surface tension. If anisotropy is big, stripes win, and you have only stripes, nothing else. So then you forget about these two phase bubbles. There are stripes. At the center of this phase diagram, this is a function of n. There is a stripe of with equal stripes of liquid and crystal with equal thickness. And near these 2 points of this phase diagram, the stripes of liquid or stripes of crystals are infinitely far away from each other. And we call it Lifshitz point. For those, I don't want to go into the semantics, but for those who know what Lifshitz point is for in phase transitions, it's a transition where not only amplitude of modulation goes to zero, but also period goes to infinity. This is not like this because there are two scales, so we don't know any analogy in phase transition in this scenario, but at least some feature of it is present, which is the distance between bubbles goes to infinity.
Is this a classical statement?
At this point, it's mean field statement, so it's a classical. Okay, of course, okay, that. So step by step, right? So this is a mean field statement. This is a minimization of energy, which I told you about, which is mean field energy, doesn't have neither classical nor quantum fluctuations. Now, if it is a bubbles state and distance between bubbles is infinitely large, you automatically means that such a state is destroyed by classical quantum fluctuations. You have to do something else at this point, and then by the same arguments which I started with, you have to, so bubble is a quasi-particle, so it has effective mass, and interaction between bubbles is, according to that formula, is 1 over Q. So it falls to the critical, so basically quantum fluctuations are destroyed. So again, no, they, so you have a bubble phase, so there is interaction between bubbles. So form a lattice. Then you estimate amplitude of quantum fluctuations or positions. You diverge. So it will be liquid of bubbles. But of course, at finite distance, interaction will stabilize it and it will be something else. Now, so if interaction is isotropic, if surface energy is isotropic, bubble phase wins over stripe phase by just a number. So it's a numerical statement. If it's strongly isotropic, there is only stripe phase. Stripe phase is not destroyed by quantum fluctuations because it's a lines. So quantum fluctuations don't destroy. Classical do destroy.
Boris,
Yeah.
see, I want to understand this a bit. So if I read the bubble phase and I introduce the quantum fluctuation, instead of having a crystal of bubbles, it will become a liquid.
Exactly. At this point, at the point when distance between them is infinity. But when you pull them close to
so if I increase the density of bubbles, what will happen?
interaction will increase and it will stabilize quantum fluctuations. It's exactly the same as initial slide, where there is particles with interaction 1 over R cubed, and then
The other question is, this is in 2D. What will happen in 3D?
very complex question which I don't want to address at all.
Sorry, maybe I didn't fully understand the answer. In the bubble phase, the described liquid phase, is there breaking of translation symmetry?
Of course.
There is.
Yes.
So it's like a crystal.
It's like super. Okay, in the context of at this point you don't distinguish between fermions and bosons. But if it's bosons, it's basically supersonic. So you basically get supersonic for free. Huh? What?
How is it then compatible with Landau's theorem?
Okay, it is not covered by Landau's theorem. So Landau's theorem doesn't cover Lifshitz points. So it's interesting. Yeah, because period goes to period. It's also a delicate question. You see that there are a lot of delicate questions here, which I may address, but I want to it's a review talk, so what can I do? If you decide to speak about what is this, I'm happy. But I'm saying that I just wanted to make a statement. Landau's theory doesn't cover it. That's an interesting point. Interesting detail.
Due to long-range interaction? Why Landau?
No, it's because it's because when you think about first place, how do you prove this Landau theory? You construct Ginzburg function and see that there is a cubic invariant there. Now, first thing which you have to look at what is the Ginzburg functional for Lifshitz point. It is higher in derivatives to begin with. Second thing is that in this particular context, construction of Ginzburg-Landau functional is very non-trivial story because there are two scales. You see what I mean? So it's not a period which goes to zero. It's distance between these bubbles which goes to zero. So construction of Ginzburg-Landau theory at this point is actually we don't know how to do it actually. But we do know because something goes to infinity here.
So if I have a classical system of particles with dipolar interactions, say at a finite temperature, and I increase the density, you would see these phases?
Sure. Lipid fields, as I said, lipid fields should demonstrate this phase. On the two-dimensional lipid field, look, there are double layer in single layer lipids. Single layer lipid on the surface of water demonstrates this thing.
Yeah, but those aren't, that's not a system, it's just dipolar interaction parts.
No, not only dipolar, there is a first order phase transition.
But that, I mean, if I just take classical point particles with 1/r⁻³ repulsion.
Yes, they should demonstrate. Yeah, they should demonstrate.
And, okay.
Yes, they should.
So do you expect it like in cell membranes or?
Look, I don't want to go into this because I mean I can say something about it, but it is very long story. So there is a very famous problem which goes under the umbrella of rafting in these lipid films, where this is very important. Yes, but there is a huge literature. So I don't want to speak about lipid films.
Are there like transfer sensibilities, like maturing patterns for the stripes, zigzag and house sensibility?
Look, stripes, if there is a quantum, if there is a refined concentration, they just anisotropic crystal, right? So dissolve on thicknesses. So there is interaction. I mean that it depends on what level you treat the stripes. So if you take into account that they also have a structure, it's basically anisotropic crystal.
Before the stripe, it's definitely a straight line, or fluctuations could destroy it.
As I said, look, it's again requires analysis. Quantum fluctuations don't destroy one individual stripe embedded, say, crystal embedded into the liquid.
Not the border. It's a straight line. It could be.
I understand that. I'm saying that if you consider individual stripe in the situation when density is zero, quantum fluctuations doesn't destroy long range order. You can check it. Classical do.
Can I ask a purely semantic question, but I really want to learn your opinion. The analogy...
I have a lot of slides.
Oh. I'll do it then.
So look, as I said, look, it's up to the audience. We can discuss it. But
if the semantics, then we...
it's not quite semantic. Okay, it's the question between analogy between the Lifshitz scenario in a regular system and Griffith's scenario in a disordered system, because in both cases the transition is driven by extremely rare inclusions. In this case, your period goes to infinity and your bubbles can be considered as extremely rare inclusion, so it's a kind of crisis of macroscopicity. So in between you have a regular phase.
As I said, at this point, quantum fluctuations destroy bubble phase, doesn't destroy stripe phase. Now, what substitutes it? We can discuss. It's a complicated question, but no question that at this point, quantum fluctuations destroys bubble phase.
Oh, they do destroy, because I was thinking...
They do destroy bubble phase. So you have to shift it here. So, in effect, this motivates next slide. So the point is the following, that, okay, if you think about consequences of this phase diagram, so you destroy by quantum fluctuations at this point, but here it is stable. So you have to say something, what happens in between, right? Also, you have to say what happens as you go between stripe and bubble phase, because it's also first order phase transition, which is also forbidden by the symmetry. And so initially we thought about bubbles of stripes, stripes of bubbles, and actually this question is still absolutely open. And in principle, it is not impossible, and actually it was our opinion, original opinion, that there is an infinite number of phase transition on the mean-field level, because you don't see how to end it. So, but then there is one model about which I would like to only mention briefly, is the following, that the problem with this is you don't know what is anisotropy of surface tension. So you have to have some simple solvable model. One of the simple solvable model is weak crystallization, weak first order phase transition, which is first order but close to second one with dipolar interaction. And this is Hamiltonian, this is order parameter, this is a density, this linear term guarantees to you that it is first order phase transition, This is solvable problem. When it is first order close to second one, by standard methods, the same thing how weak crystallization theory goes, and you see the following, that you immediately see that there are several phases: stripe, hexagon, which is basically bubble phase, stripes, hexagon, crystal. The question is, how do you go between these two? Answer, you can calculate surface tension. This is very anisotropic. So you will end this sequence by having another two phases. So the lesson is that there are intermediate phases between crystal and liquid, and sometimes in some models it's a finite number of them, and they have Lifshitz points. It's either bubbles or stripes or combination of them, but finite number. Okay. Now these are conclusions of this first part. Just take home, that there are such phases. And so for free you have, so if it's Fermi liquids, then you have to work a little bit more, but for Bose liquids, it's basically supersolid phases. All of them, by the way. So my definition of supersolid phase is that when number of maxima in density, modulation, and number of atoms in the system are different. And in all these phases, it's obviously the case. If you just embed bubble of liquid crystal in the liquid, it's still a liquid, it can flow. So.
Maybe we can make the following arrangement. Why don't we, since there was some intermediate conclusions, why don't we go for lunch now and then continue?
Can you give me another 5 minutes and then I will let you go for lunch? Because it's not. It's a.
Sure.
Okay, can I do the same thing but in 5 minutes?
Sure. Yeah.
Why not? Okay. Give me 5 minutes. Come on.
Exceptional.
No, lunch is important.
Yeah, sure, yeah.
Okay. Now, I would like to say the following.
Very enjoyable weather
By the way,
at the moment.
This is for my time.
Yeah, but of course, the truly great scientists get talks, but their time is spent now.
You have to repeat.
I'll tell you
Tell me. Yeah, sure. So I would like to say the following, that all of this was very simple for dipolar case. For Coulomb case, if you don't take into account surface tension, there is no phase separation to begin with. Because if you phase separate, why do you have phase separation? Because density changes. You pay for density a lot of energy. So this phase separation for Coulomb case happens because surface energy is negative. And so the proof of this is actually quite complicated, but I just would like to say that with this comment, everything which I told you above, after hard work, applies for Coulomb interaction as well. So that's one story, one thing. And then I would like to say what I'm going to speak about, if I would be allowed to do so. There are two other, so I decided to speak about three very simple ideas. First idea I already told you about. Second idea is the following, that in the case of Fermi system, the question is what happens in magnetic field and what happens in the function of temperature. And of course, we can discuss this subtle theoretical details about long-range order and all of this, but there is much more robust, aspects of this, which is called Pomeranchuk effect, which is the fact that entropy of liquid and entropy of crystal is different. In entropy of liquid, of crystal, absorbed temperature is larger than entropy of liquid. As a result, crystal grows, as temperature increases, and crystal grows and magnetic field increases. And there are experimental data which supports this idea. So this is one idea which So I just wanted to give you opportunity not to listen if you don't want to. And second idea, which is also very important, is that when you go to even higher temperature, all of this, by the way, happens near in the border between crystal and liquid. And where it is in terms of RS. And RS is very big, say 40. It means that when crystal melts, you still have a liquid. Now the question, what is this liquid? On the one hand, so I use the term which is coined by Andreev, which is called the semi-quantum liquid. It's the following, that usually in Fermi systems, plasma frequency is the largest one, then there is interaction energy, which is smaller than plasma frequency, then there is the Fermi energy, which is smallest one. So when you increase temperature above Fermi energy, you go to the gas. Now, in these systems, Fermi energy is smaller than the bifrequency. In the bifrequency, or plasma frequency in the electron context, plasma frequency is smaller than interaction energy. As a result, or when you increase temperature above Fermi energy or above melting temperature of the crystal, your temperature is still much smaller than the bifrequency or plasma frequency, and also much smaller than interaction energy. So you have a liquid which is not degenerate because temperature is larger than Fermi energy. It is not classical because it is not a gas, of course, because temperature is smaller than interaction energy. It is not also classical because temperature is smaller than plasma frequency. So most of the installations are not excited. So what is it? And and this plus experiments will constitute the rest of the talk, if it will take place. So that's it. You're released.
For those who arrived later, so today is a special day, it's holiday, so all restaurants are closed. But
You don't have to apologize.
The green place will be open especially for us, so we should all together now.
What note do you take? Do we all take the most input, or do we take one of the?
I'm worried that we are in the fluctuation region, because you see, you have this scale only in the region around it. There is no scale, right? I believe it's
The code is 1, 2, 3, 4. You need the code today to use your entrance card. It's 1, 2, 3, 4.
So you do the There's high security here. Yeah. When you started,
I said that.
The maximum there is no.
Yeah, but it's just telling you why I'm pointing out. No one has seen that. Oh, no one has seen this. Yes, to point out. Look at this.
Next stage.
Please follow me. It's very fun.
N times A and the critical point is 2n.
Yeah, no, sure.
And it's exactly something.
Regime. It's just, two is very simple. It's just
Yes, yes, and I felt so odd.
take n squared and do the a big theory. The average of n squared is 2 of n squared. And in constant you don't have this.
Yes, where's the third?
That's why. Oh, this is
Okay, that makes a lot of sense.
yeah, it's already.
So it has to go up.
Yes, and then that's
And then it of course goes down.
basically
For different reasons, I guess.
you know, actually, there is something which depends on how chemical potential goes. So you didn't hear about the sound, people normally do not discuss what happens to the body. What happens to the body of
Electromagnetism, that one, the most, the ones I want to have. I never thought I took just from geometry
and the pressure. The chemical potential is supposed to be bound in the same. Then I ask you a question: what happens to the particles?
I would say
You open
really juicy.
the particles, the flow will be and the average sources. When you increase the temperature, actually particles are supposed to go towards the equator. That's how the chamber is isolated open. Actually, in weakly reacting gas and in your system, the particles, when the whole equilibrium go outside.
No,
it's inside only the open.
In some sense,
and
that's
the sign of
depends
on
Up or down temperature.
whenever it goes up, the particles will go outside.
Away from, yeah.
And only then they will return back. When
I got it close next, so this is a slogan.
So kind of this behavior is relevant.
That's cute. So without the hole.
Yeah, there are all these classical instabilities of like terrain patterns, stripes, right? These transverse disabilities, and I wonder if they show up in these electronics systems.
I think
there you have real diffusive dynamics typically that give you things like this.
The part of the skip is really quite interesting. This is this clever idea that because this is contentious. Some people do not. Some people want to start from the thermal liquid and just sum up diagrams and glue in place to get there.
Yeah.
But these guys, that makes much more sense. I mean, they start from sort of stronger correlated aspects. So he has a very clear prediction, which is quite clever. Which is he would say, imagine that you are in a regime where you
he applies an in-plane field, the connectivity goes up. Why? Presumably because his momentum effect is gone. You see, so what he wants to say is that liquid has lower entropy than solid. Presumably because there's a spin on each side of the solid.
Yeah.
But that's not true if you quench it with field. Also, I said it the wrong way. The connectivity will go down as I put an in-plane field. Because you see, he will replace the liquid with the solid.
Oh, okay.
So, and I think that's seen.
I mean, if Boris, does his, diagram Monte Carlo for these sorts of systems,
This is the fixed node.
Look at the.
You mean the fixed node?
No, it's what he talked about the other day. Gave the diagram Monte Carlo.
Oh, I see.
With the.
I'm sure they can go that far.
Cooling system. Can you see?
I'm not sure they can go that far, right?
And density, plane, and smooth.
So I heard that talk. I missed it last time because of jet lag. But I heard this talk in Amsterdam, and if I remember correctly, they cannot push it all the way.
No, but like
diagrams, something like that.
Yeah, like Tentori or something. He said. I don't know if they do anything else, but we saw how. Even the bare part was reproducing stuff on this unitary limit injects down in case.
Was it bare?
That was the bare diagram, and then he does this sort of.
Bare diagrams of phase order.
Yeah, and then he does this sort of normalized guys and
it's a good point.
But I wonder if he could stretch it.
It's a good point. Well, how would you see a crystalline diagram, macroemulsion diagram? After all, it's dirt. It makes an assumption that there is some sort of adiabatic continuity. See, I don't know if they can get that.
If they can get free energy, can you get a free energy and sort of see that you need to.
The question: can they see
broken construction?
Can they see broken symmetry with their diagrammatics? And so I'm not sure. They would have to do it. They would have to put it in, I think, by hand or something.
I was thinking, can he see phase separation? If you plug free energy, shouldn't you see that? I'm worried about this. The bubbles are like they're phase separation, right?
Well, on some sort of microscopic scale, though.
Yeah. Well, I guess it is some
intermediate.
frustration.
Yeah. But so the point is actually very simple. It's the old Anderson's point that trying to do what was it, Gell-Mann record. They were working out the energy of the cool gas.
Yeah. It's trying to see the phase transition.
That's the wrong thing to do. It's not going to work. Yeah. So I'm worried that the diagrammatic Monte Carlo is the same thing. It's just a better way of doing diagrams.
Yeah.
And if you're doing diagrams, you're doing that way here. Yeah. Although this resummation stuff, that may.
Yeah. Right.
I don't know.
Well, I suppose that then you could also do things like Pade and stuff. And try to, if you think that there is a phase transition. That's no.
Yeah.
It's probably hopeless, but I'm just wondering if there's anything. Because as you say, it is somewhat contentious. It would be nice to have some more.
I think experimental would be better. If you could see this stuff.
Yeah.
With something like Americovi's local ICT. The scanning compressibility.
Yeah, so capacity. it like in Chicago when you left, Jim?
It was cold, but we had just come off of a warm spell, so we had about this much snow until about 5 days ago.
Yeah.
And then it kind of melted down. But it's colder there than it is here.
Is it?
Yeah.
At least you have the Bears to root for.
I know, man. I was so disappointed that they dropped that one to Green Bay. I guess your Chargers haven't set the world.
What a disaster.
Yeah.
Best team ever to make the playoffs. They're the best team ever to not make the playoffs, I should say. Yeah.
I like your quarterback, though.
He's great. He's going to be some good receivers, good tight end. But they screwed up early in the year. I'm a Jets fan, though. So.
I like the Jets also, but I don't like them more than the Bears.
Yeah, well.
I like the Bears style football, though.
Yeah.
Rough and tumble.
Yeah. I don't know. It's you know, they need a. Well, I don't know. I guess you know,
Well, they're inconsistent. They haven't got it all clicking, and Cutler is a little bit of a wild man.
Yeah, I'm not sure he's really the quarterback of the future for the Bears, but
I think he can be. Man, he's got one rocket arm. You know, he's got an arm like Rivers, but he doesn't quite have the same field of vision.
Yeah.
He doesn't see the field quite as well. But he's tough as nails.
well, I wouldn't mind seeing the Bears do well. It's hard to imagine anyone anyone
Touching
in
a
the
New
NFC
England
team could beat New England or Pittsburgh. Though. I mean, I really don't.
I don't know. I think the Bears match up better against Pittsburgh than they do New England.
New England's been looking really good.
Yeah, they just virtually never make a mistake.
Yeah. Yeah, I'm tempted to put on my coat just looking outside the window. It makes me want to put on the coat. So you don't vote in the mayoral election, do you, for Chicago? Where do you live?
Live Evanston, yeah.
Okay, so that's that. You don't vote for Chicago mayor?
No. I would like to.
I remember when I was postdoc there. It was just the weirdest things would happen in Chicago.
Man, I know it is bizarre. Well, the whole thing of.
That's when Harold Washington suddenly died.
Oh God, yes,
Yeah.
yeah. He was, well, it's a. We've got a bunch of clowns out there right at the moment. The whole thing is everybody's trying to position themselves to keep. What's his name? He was.
Ron Emanuel.
Yeah, Ron Emanuel off the ballot.
But I thought they ruled he could be on the ballot. I thought he was cleared.
He's clear, but I mean the machinations that were taking place to try and prevent him from getting on there.
after Washington had died,
Yeah.
there's some brouhaha because some students at the Art Institute or someone had made a painting, a giant painting of Harold Washington wearing women's underwear. And then this greatly offended some of the one or more of the aldermen who were Washington's supporters, and so they like marched down to the Art Institute and had the painting confiscated.
Yes. Yes.
It was a ridiculous play.
Vaguely.
I really wanted to go see the painting. Actually, pity Washington seemed to be a pretty effective mayor.
Yeah.
But I don't know, Daley, I guess, was.
I think Daley completely surprised me.
Yeah. In a good way.
In a good way, and I think he surprised everybody, many people in a good way. He
People
really
assumed
cares
he'd be
about the
totally
city.
corrupt, and
He loves the city, and
Yeah.
he does his best to help the city. And there's corruption going on somewhere down the line, and deals are made. But that's Chicago.
Yeah.
But I don't know. I think he did really well for Chicago. He's the most inarticulate guy I've ever heard. But
Yeah. Well, you heard George Bush read.
yeah, well, that's true. That's true. I should second most inarticulate. Yeah, was there any announcement about whether there's a change in the schedule at all this afternoon?
I don't recall.
Yeah, I think so. So the talk by Paul Goldberg is cancelled, and I think it's replaced by Vincent Liu.
Oh, okay.
And I'm not sure about the order, though. I think Vincent Liu may be giving the last talk.
Okay, thank you.
Sure.
That's too bad. I was hoping to see Paul.
So we're ending early then today.
No, I don't
think
No,
so.
same time.
Well,
Because there's one canceled, one.
oh, there was no Winston was canceled.
Vincent was canceled originally.
Yeah. Yeah. And did you?
Yeah, I was there. Did you understand what he was saying? That there's a break in the slope?
Sorry, break the slope of which?
And the direct point?
Break the slope of what? I forgot.
Oh, he was showing this, I think it was STM actually, where it was very asymmetric. It was
Oh, yes, yeah, right.
It was on a scale of 100 MeV.
Well, yeah.
Or so, but, I mean, it didn't...
That STM is a high energy, that asymmetry is very high energy asymmetry.
He was somehow implying that it pushes all the way down.
Yeah.
And then in fact that you have cone like this down,
yeah,
and a cone like, let's say this, with a different
opening angle.
Yeah, yeah. I don't know why it's impossible. There's no way.
How do you do that? How do you make a band structure?
It's impossible. You see, all that can happen is that it has to have a k-dot.
Yeah,
So you
yeah.
have
If it's an analytic,
it has to be.
Yeah.
And then the next one is k squared. So that they appear.
Right.
still working on graphene?
Yeah, a bit, actually. Something done with Paco and some experimental, some tri-layer calculation, but nothing really exciting. Nothing really exciting. Finishing something up with Misha Fogel and some tri-layers. Nothing really.
Did you see my work on the biolayer?
Yeah, I actually. Are you going to talk anything about that? Yeah. Okay, good.
You see, have some concerns? Or?
No. I mean, being able to do RG is the these things is the way to go.
I think so.
Yeah. It seems to be a really very powerful way of investigating probably all the possible instabilities and.
I'm not sure about all possible, but at least the most obvious.
Okay, yeah, right. You can always embed some
yes.
high periodicity here or something.
Yeah.
Right. Yeah, have you looked at what Alan has been doing in the there?
Before or after?
No, I'm just
So they looked at something. It's similar in spirit, but it's actually implemented very different ways, and they get different results. Actually, and I actually disagree with many things they said.
Are you going to mention that?
No, I'm not going to mention one.
Can I ask you about it?
Okay, so I will mention a phase that they have been discussing, which does come out in a specific model, in my opinion, in a very controlled way. Anyway, so for instance, there's a way to classify how many contact couplings you can get